In this video, we're going to learn how to calculate with forces. I'm just kind of doing a voiceover because the original audio was really bad, so hopefully I can stay with it. So there are four fundamental forces in physics that you can see below. We're mostly going to be worried about the electromagnetic and the gravitational force in this class. We certainly, if we have time, we can learn more about particle physics, which gets into the strong and weak nuclear force. So mainly it's the electromagnetic and the gravitational force that we're going to be worried about in this class. Apparently I must have talked a lot about this the first time going through. Don't know why. And still going. I would have tell a joke or something about forces, but I guess I can't think of any at the moment. Hey, I'm moving on. All right, sorry about that. So, when dealing with forces, we have Newton's three laws of motion. The first law has to do with an object that doesn't have forces and how it responds to no forces or how it responds to an unbalanced force. So if there are no forces on an object, or if there are balanced forces on an object, the object will not accelerate. And then when there is an unbalanced force on an object, then the second law applies, and the acceleration will be in response to that force. The bigger the force, the bigger the acceleration. And the third law is for every force there's an equal and opposite force, and we'll get into that more. So with the first law, some examples of where we'd see the first law would be a magician pulling out a tablecloth. The objects on that tablecloth are at rest, and if you pull on that tablecloth, they remain at rest. If you're on a sled and you hit a patch of dirt, the rider is in motion, and they will continue in motion by flying off of the sled. So the sled has a force on it, but you as the rider do not have a force to stop you. So those are how we see the first law in action, that inertia, the resistance to change. In terms of the second law, again, it's how your force, mass, and acceleration are related to each other. And to make sure we know the unit of force is the Newton, and a Newton is equal to 1 kilogram meter per second squared. Since that's kind of cumbersome to write, we come up with this new unit, newtons. So basically, we can all imagine, well, if we have a really massive truck versus a car and they have the same size engine, the car will be able to accelerate faster given the same force from the same engine. If you have a greater force, like a bigger engine in a similar size car, you can have greater acceleration from the greater force that comes along with that. So F equals ma is probably kind of a familiar to us. And here in this video, we can just see an illustration of how as the force changes, and so the blue arrow represents the force, and I believe the green arrow represents the acceleration. As soon as the push is stopped, the book no longer accelerated, it just moved off with a constant speed. So then just resetting this here. Now if I go to a more massive object like a file cabinet, if I push on the file cabinet with a similar force to the book, the file cabinet will also accelerate because there's an unbalanced force, but much less so, and it takes a much greater force on the file cabinet to get it to accelerate. And again, you can see as soon as that force is gone, the acceleration stops and it just moves on with a constant speed, unlike the real world where there's friction. So this second law is a really important formula in physics, and you gotta make sure you know it. The third law is that every time one object puts a force on another, that second object puts a force back on the first object. So if we think of a horse pulling a cart, if the horse puts a forward force on the cart, by Newton's third law, the cart must put a backwards force on the horse. Of course. Okay, these two forces, the green force and the red force, the green force is the horse on the cart. The red force is the force on the horse. These two forces are on two different objects, and as they are on two different objects, they cannot cancel each other out. They are equal and opposite, but they can't cancel each other out because they're on two different objects. Okay, and that's a common misconception with the third law, is that these should be able to cancel each other out, but they can't. They're on two different objects. So if we look at how is the force able to move the horse and the cart forward, since there's a backwards force on the horse, if the horse is moving forward, there must be a forwards force on that horse. So the forward force on the horse comes from the ground, and that's actually the responding force to the force that the horse is putting backwards on the ground. So the horse pushes backwards on the ground, and the ground responds by pushing forward on the horse, which then when we compare the backwards force on the horse to the forwards force on the horse, as long as the forwards force is greater than the backwards force, the horse will accelerate. Okay, if they're balanced, then the horse will not. At this point, I want to point out the difference between mass and weight. Mass is measured in kilograms, and it's basically how an object resists any change in motion. And your mass is the same no matter where you are. Weight is the force of gravity. So when we label forces in physics, we don't label a force as gravity, we label it as weight, because weight is the force of gravity. Weight is measured in newtons in physics, and it depends on the strength of the field. One thing that should be pointed out here is weight is equal to the object's mass times the acceleration due to gravity. So here on Earth, that would be your mass in kilograms times 9.8 meters per second squared will give you your weight in newtons. A newton is roughly equal to about a quarter pound. I believe it's about closer to 0.23 pounds. So like a quarter pounder is about, could also be called a Newton burger. Whenever two surfaces in contact, there will always be friction between the two forces, and there's two types of friction. There's static friction, which is the friction it takes that you need to overcome to get something moving. And then there's the sliding friction, which is the type of friction that resists an object once it is moving. And so both of them can be described by the really fun formula here, which is the force of friction is equal to the coefficient of friction times normal force. And so basically this coefficient of friction has to do with the two surfaces that are in contact. The normal force is equal to how strongly those two objects are pushed together. And then the force of friction is, again, that resistance force. The coefficient of friction will be different if you're talking about static versus sliding friction. And the coefficient of friction is always greater for static than it is for sliding. So it's always harder to get something moving than it is to keep it moving, is basically one way of looking at that. So when we're solving force problems, it's always important to draw pictures so that you have all the forces on the object labeled. So you're never going to be right if you can't label all the forces on the object. You want to write out Newton's second law for each relevant direction. So whether you're talking about horizontal motion or vertical motion, left to right motion, up to down motion, you just need to make sure you have. And then once you have that, you can solve for the needed quantity based on that. So I believe I'm going to work a few examples here. All right, so if we look at a shot putter exerting a force on a shot, the shot has an acceleration of 19 meters per second squared, and we want to know what is the mass of the shot. So if we look at, we've got a picture here of a shot putter. Now just having a picture isn't going to help. We have to put the forces in on this. Okay, so hopefully I'm going to get to that pretty quickly here where we get forces. There we go. So the shot putter is putting a force forward on the shot put. And really, there should be more forces in this. I think I probably made this oversimplified unless I'm getting to it, but there really is a downward force of weight on the shot put. But right now we're just going to pretend like that's not there. And just look at the force of the shot putter. We're pretending is the only force on the shot put, so maybe he's throwing the shot in space. And that's going to equal to the mass times acceleration. Okay. So we have 140 newtons equals the object's mass times its acceleration, and solving for m then gives us a mass of 7.4 kilograms. If you want to look at this, if we have a sled that's being pulled across a cement sidewalk at a constant speed, I don't know why you do that, but let's say you are. We need a force of 36 newtons to make this happen. And we want to know what's the coefficient of sliding friction between the sidewalk and the metal runners. So as we go to, first we need a picture, we need to put all the forces on. So we've got a forward force, backwards, so forward force is being exerted of 36 newtons. If the sled is going at a constant speed, that means all the forces balance out. So we've got the downward force of gravity is being countered by the upwards normal force. So the downward force is green. The upward normal force of the cement sidewalk pushing up on the sled is the yellow. The forward force of the person pulling on the rope is the blue. And then the backwards force of friction is the red. So again, all these forces have to be equaled out. So we write second law, we're going to write it for each direction that's important. So we have a horizontal force, which is the net force is equal to the applied, the blue force, minus the friction force, the red one. And again, it's minus friction because friction is against motion. And that's equal to the mass times your acceleration in the horizontal or the x direction. And then in the vertical direction, we have the net force is equal to the normal minus the weight. So the normal, again, is the yellow force, and the weight is the green. And that equals the sled's mass times its acceleration in the y direction. So now we can, once we have this, we can plug in all our known values. And so we know that the applied force is 36 newtons, and in the horizontal direction we're not accelerating, so A equals 0. So that means the force of friction must equal 36 newtons. The normal force minus 56 newtons, and I realize it's supposed to be 52, is what the problem stated, is also equal to mass times 0 because it's not accelerating the up and down direction. So the normal force must also be 56 newtons or 52 if you use what's originally stated in the problem. And then we know since the force of friction is equal to the coefficient of friction times the normal force, we can see that 36 newtons must equal that mu letter times 52 newtons. So mu, once you do the algebra to solve, mu then is equal to 0.69. And mu is a unitless quantity. Because you newtons divided by newtons, they cancel out and you're left unitless.
In our third and final example,
so we have an example here, and this is a pretty common thing in physics. It's sometimes hard to understand where if you have somebody being accelerated in an elevator and we look at what is the scale going to read. Again, we need to look at a picture of this. In the elevator, you're going to have two different forces on you. You're going to have an upwards force from the scale you're standing on, which is being represented in green. That's the normal force. And then a downwards force of gravity, which is being colored in blue here. So that's the only direction we need to worry about in an elevator problem. And again, the net force, that normal force in the upwards direction minus the force of weight, is going to be equal to the mass times acceleration of the person in the elevator. So again, normal minus weight, green minus blue, equals mass times acceleration. We do not know the normal force. We can figure out the weight. The person's weight is always m times g. So we take 50 kilograms as their mass times the acceleration due to gravity. So the weight's 490 newtons. So now we know normal minus 490 is equal to the 50 kilogram mass times that the acceleration given the problem, and we can solve for what the normal force must have been. Okay. Talking about falling objects a little bit, the force of air, unlike friction, is speed dependent. So the faster you go, the more force there is. So when something is falling in air, it eventually will reach a speed where that drag force has increased to equal out the weight. And that's how objects reach terminal velocity when they fall in air. Okay, so that's it for this video. Hope this helped.